For nearly a year after Allied forces landed in Normandy, German tank crews repeated the same conclusion in report after report. American tanks were fast, they were reliable, they appeared in overwhelming numbers, but one-on-one, they simply weren't dangerous enough. The M4 Sherman, the backbone of America's armored forces, had earned a reputation that frustrated both its crews and its commanders. Against Germany's Panther and Tiger tanks, the Sherman often had to rely on superior numbers, air support, or clever tactics to survive. German engineers believed they understood American tank philosophy. They assumed the United States preferred quantity over armor, mechanical reliability over firepower, and production speed over technical sophistication. To them, American industry could build thousands of tanks, but it could not produce one capable of matching Germany's finest machines. Then, in the final months of the war, a new American tank appeared on the battlefield. At first, many German soldiers assumed it was simply another Sherman with minor improvements. They were wrong. When German engineers finally examined the vehicle closely, they discovered something they had not expected. America had finally built a tank that demanded serious respect. By February 1945, the Third Reich was collapsing on every front. Soviet armies were smashing through eastern Germany, while American, British, Canadian, and French forces pushed relentlessly from the west. Fuel shortages crippled German armored divisions. Factories struggled to produce replacement vehicles as Allied bombers devastated transportation networks. Experienced tank crews had become increasingly difficult to replace. Every new battle reduced Germany's remaining armored strength, yet military engineers continued searching desperately for technical advantages that might slow the Allied advance. German armored doctrine had always emphasized battlefield superiority through engineering. The Panther, introduced in 1943, combined sloped frontal armor with a powerful high-velocity 75mm gun capable of destroying most Allied tanks at long range. The Tiger I carried even thicker armor, and the famous 88mm cannon that had become legendary among both German crews and Allied soldiers. Later came the King Tiger, an even larger machine whose armor appeared almost invulnerable from the front under ideal conditions. Although these vehicles suffered from mechanical problems and complex maintenance requirements, German engineers remained convinced they represented the highest level of tank design in the world. American tank development followed a very different philosophy. Rather than pursuing the heaviest possible vehicle, American planners emphasized reliability, mobility, standardized parts, and mass production. A tank that reached the battlefield consistently, remained operational for weeks, and could be repaired quickly often proved more valuable than a technically superior machine constantly sidelined by mechanical failures. This philosophy produced the Sherman, a tank that became one of the most successful armored vehicles ever built. Yet success came with criticism. As German armor improved during the war, Sherman crews increasingly found themselves facing opponents with thicker armor and more powerful guns. Reports from North Africa, Italy, and later France repeatedly highlighted the same problem. American tank crews could defeat Panthers and Tigers, but doing so often required numerical superiority or tactical advantages. Direct frontal engagements favored the German machines. Tank commanders requested a vehicle capable of matching German armor without depending upon overwhelming numbers. Interestingly, the concept already existed. Long before American troops landed in Normandy, engineers in the United States had begun developing a heavier tank designed specifically to replace the Sherman eventually. The project evolved through numerous experimental designs before becoming what would later be known as the M26 Pershing. Development moved more slowly than many officers wanted. Part of the delay resulted from disagreement inside the American Army itself. Some senior commanders believed existing Shermans remained sufficient when combined with artillery, aircraft, and aggressive maneuver tactics. Others feared introducing a heavier tank would complicate logistics, reduce mobility, and slow the rapid advances that had become central to American operational doctrine. General George S.N. Patton belonged firmly to this second group. Patton valued speed above almost everything else. He worried that heavier tanks consumed more fuel, crossed fewer bridges, and demanded greater maintenance. From his perspective, a fast-moving army supported by reliable medium tanks could defeat almost any opponent through superior maneuver rather than superior armor. Other commanders strongly disagreed. Combat experience in Normandy had revealed just how dangerous Panthers could become when defending favorable terrain. Thick hedgerows, narrow roads, and limited visibility often prevented German crews from exploiting their numerical advantages. German guns destroyed American tanks from distances where return fire proved ineffective. The debate continued for months. Meanwhile, American engineers refined the Pershing. Unlike the Sherman, the new vehicle carried significantly thicker armor, a torsion bar suspension that improved ride quality over rough terrain, and most importantly, a powerful 90mm gun capable of engaging Panthers and Tigers on much more equal terms. Even so, production remained limited. By the time the first Pershings finally reached Europe in early 1945, Germany was already nearing defeat. Only a small number arrived before the war ended. Their appearance surprised many German units because intelligence reports had provided relatively little information about America's newest tank. German commanders expected another Sherman variant rather than an entirely different design. The first battlefield encounters generated immediate curiosity. German soldiers quickly noticed the unfamiliar turret shape. The hull looked larger than a Sherman. The gun appeared considerably longer. Some initially misidentified it as an experimental British vehicle. Others assumed American forces had simply modified existing Shermans with heavier armor. Only after closer examination did they realize they faced an entirely new tank. One of the most famous engagements occurred near Cologne in March 1945. American forces advancing through the city encountered a German Panther defending an intersection near the cathedral. Cameras belonging to Army Signal Corps photographers captured the remarkable duel on film. During the engagement, one Pershing maneuvered into position and fired several rounds that destroyed the Panther. The footage became one of the most famous tank combat recordings of the Second World War. To modern viewers, it demonstrates the Pershing's firepower. To German observers at the time, it suggested something equally significant. The Americans finally possessed a tank capable of defeating a Panther without relying entirely on luck or overwhelming numbers. Elsewhere along the Western Front, several Pershings suffered damage or were temporarily abandoned during combat. These incidents provided opportunities for German recovery teams and technical personnel to inspect the new vehicle whenever battlefield conditions permitted. German engineers approached every captured Allied weapon systematically. Throughout the war they had examined Soviet T-34s, British Churchills, American Shermans, anti-tank guns, aircraft, radar equipment, and countless smaller weapons. Every captured machine represented an opportunity to understand enemy engineering decisions. The Pershing received exactly the same treatment. Initial inspections focused upon external features. The first surprise involved proportions. Many engineers expected the Americans simply to enlarge the Sherman. Instead, they discovered an entirely different layout. The Pershing possessed a noticeably lower profile than expected for its size. Its turret offered improved protection while presenting a smaller target. Hull lines reflected careful attention to ballistic shaping rather than simple vertical armor plates. Although not as aggressively sloped as the Soviet T-34, the Pershing demonstrated that American designers had clearly incorporated lessons learned throughout the war. Armor thickness became the next subject of examination. German specialists measured frontal plates carefully. The Pershing's glasses combined respectable thickness with moderate sloping, increasing effective resistance against incoming shells. While not matching the immense frontal armor of the King Tiger, it represented a substantial improvement over earlier American tanks. Engineers recognized immediately that standard German anti-tank weapons could still penetrate the Pershing under favorable conditions. Yet they also understood something important. Destroying this new American tank would require considerably more effort than destroying a Sherman. That realization alone marked a major change. Firepower attracted even greater interest. German ordnance experts carefully examined the 90mm main gun. The weapon differed significantly from previous American tank guns. Longer barrel length suggested higher muzzle velocity. The breech mechanism reflected modern engineering principles emphasizing both strength and efficient operation. Ammunition storage demonstrated thoughtful internal organization that balanced crew accessibility with safety considerations. When calculations began comparing ballistic performance against existing German guns, the results surprised several analysts. Although the famous German 88mm weapons still retained certain advantages depending upon ammunition type and engagement range, the gap had narrowed dramatically. America no longer relied upon an underpowered medium gun. The Pershing could threaten Panthers directly against Tigers. It finally possessed realistic opportunities during frontal engagements. especially at moderate combat ranges. This represented a profound shift in battlefield expectations. Crew ergonomics also drew attention. German tank interiors often reflected engineering priorities focused upon minimizing vehicle size. The result frequently produced cramped working conditions. The Pershing appeared noticeably more spacious. Crew positions allowed relatively comfortable movement. Control arrangements demonstrated careful attention to reducing operator fatigue. Visibility from the commander's position proved particularly impressive. Cupola design offered improved observation compared with several earlier American tanks. German evaluators understood that comfortable crews often fought more effectively during prolonged operations. Mechanical systems received equally careful study. Removing access panels revealed an engine compartment organized with maintenance in mind. American engineers had clearly prioritized ease of repair. Components remained accessible. Routine servicing required fewer complicated procedures than many German vehicles demanded. This characteristic reflected one of the greatest differences between American and German engineering philosophies. German designers frequently accepted mechanical complexity if it improved battlefield performance. American designers consistently sought solutions balancing effectiveness with reliability and maintainability. The contrast became especially obvious when examining transmissions and suspension systems. The Pershing employed torsion bar suspension, a feature already familiar to German engineers through vehicles such as the Panther and Tiger. Unlike the vertical volute suspension used on most Shermans, torsion bars provided smoother travel across rough terrain while improving crew comfort and firing stability. German engineers recognized this immediately. The Americans had not merely copied existing ideas. They had adopted a suspension concept already proven effective while integrating it into their own design philosophy. Attention soon shifted toward manufacturing quality. German industry by early 1945 operated under increasingly desperate conditions. Material shortages affected steel quality. Bombing disrupted production schedules. Factories often relied upon inexperienced labor replacing skilled workers lost to military service. The Pershing reflected an entirely different industrial environment. Machining quality appeared consistently high. Welds demonstrated impressive uniformity. Cast components exhibited careful finishing. Internal fittings showed precision impossible for many German factories to achieve during the final months of the war. For engineers who had spent years struggling with wartime shortages, the difference was impossible to ignore. The tank represented not only engineering capability but industrial capacity. America possessed the ability to produce sophisticated machines in enormous quantities while Germany increasingly struggled simply to replace battlefield losses. That realization may have been more significant than any individual technical feature. A single superior tank rarely decided was an entire industrial system capable of building thousands certainly could. Some German evaluators reportedly remarked that the Pershing seemed designed by engineers who expected their vehicle to remain operational for extended campaigns rather than simply survive individual battles. Maintenance accessibility, standardized components, logical equipment placement, and overall mechanical simplicity reflected confidence in long-term logistical support. Such confidence no longer existed inside Germany. Every new tank delivered to the front faced shortages of fuel, spare parts, transport vehicles, and trained mechanics. Even brilliant engineering became meaningless when armies lacked resources to sustain it. As reports concerning the Pershing circulated among German technical offices, a subtle but important conclusion began emerging. The Americans had not attempted to build another Tiger. They had not attempted to copy the Panther either. Instead, they had created something uniquely American, a heavy tank balancing protection, firepower, mobility, reliability, and production efficiency without pursuing extremes in any single category. For engineers accustomed to evaluating vehicles primarily through armor thickness and gun performance, this broader philosophy proved increasingly difficult to dismiss. The Pershing represented something Germany had underestimated throughout the war. American industry had learned from every battlefield experience. It had studied enemy technology carefully. And although the new tank arrived too late to influence the overall outcome of the conflict significantly, its design suggested the direction American armored warfare would take in the years ahead. For German engineers examining captured examples amid the ruins of the collapsing Reich, that realization raised an uncomfortable question. If this was only America's first true heavy battlefield tank, what might the next generation look like? Once the United States turned its full industrial power toward the post-war world, the more German engineers examined the Pershing, the more they realized that it represented a fundamental shift in American armored doctrine. Throughout most of the war, German intelligence had characterized American tank design as conservative. Sherman tanks were considered dependable, mechanically simple, and easy to manufacture, but rarely revolutionary. German technical reports often concluded that American designers willingly sacrificed armor protection and firepower in exchange for reliability and production speed. Those assumptions had become deeply rooted within the Wehrmacht. The Pershing forced engineers to reconsider nearly every one of them. One of the first detailed studies focused on the vehicle's armor layout. German engineers had spent years refining the science of ballistic protection. Every degree of armor slope mattered. Every weld, casting, and structural joint influenced a shell's chances of penetrating the hull. During the war, Germany had pioneered many advances in sloped armor, particularly with the Panther. When engineers measured the Pershing's glacis plate, they found that American designers had carefully balanced thickness and angle instead of simply increasing armor weight. Unlike the Tiger I, which relied primarily on thick vertical armor, the Pershing used moderate sloping to improve effective protection without dramatically increasing the vehicle's weight. It was not revolutionary, but it demonstrated that American engineers had fully absorbed the lessons that German and Soviet tanks had taught throughout the war. Several engineers reportedly noted that while the Pershing's armor would not guarantee survival against every German anti-tank weapon, it significantly reduced vulnerabilities that had plagued earlier Shermans. The front hull no longer represented an easy target for medium-caliber guns at typical combat distances. German tank crews would now need better positioning and more accurate shooting to achieve successful penetrations. The turret attracted even greater interest. German engineers had always viewed turret design as one of the most difficult aspects of armored vehicle engineering. It had to provide maximum protection while allowing sufficient space for crew members, ammunition, communications equipment, and the main gun's recoil system. The Pershing's turret impressed many observers because it avoided unnecessary complexity. Its cast construction produced smooth, rounded surfaces that naturally deflected incoming projectiles more effectively than flat armor plates. The rounded mantlet surrounding the main gun minimized weak points while simplifying manufacturing. Compared to many earlier Allied tanks, the turret appeared remarkably modern. Inside, German specialists examined crew positions carefully. The loader enjoyed noticeably more working room than inside a Panther. The gunner possessed well-arranged controls. The commander benefited from excellent visibility through an improved cupola equipped with multiple vision blocks. This seemingly minor feature drew considerable attention. German commanders had often complained about restricted visibility inside their own vehicles, particularly during close combat in cities or forests where threats could emerge from several directions simultaneously. The Pershing's commander could observe the battlefield far more effectively without exposing himself unnecessarily. Good visibility often determined survival long before armor thickness became relevant. Another subject fascinated German ordnance experts almost immediately: the 90mm ammunition. American engineers had designed several different shell types for the Pershing's main gun, each intended for specific battlefield situations. Armor-piercing rounds offered improved penetration against enemy tanks, while high-explosive ammunition remained effective against infantry positions, bunkers, and lightly armored vehicles. German specialists compared these shells with ammunition used by the Panther's 75mm KWK-42 and the Tiger's famous 88mm guns. Pure penetration figures told only part of the story. The 90mm shell carried considerable explosive power after penetration, increasing the likelihood of catastrophic internal damage once armor had been pierced. Crew casualties, ammunition explosions, fuel fires, and structural damage often resulted from what happened after the shell entered the vehicle rather than the penetration itself. Calculations suggested that against Panthers, the Pershing possessed a genuine chance of success even in engagements where Shermans had previously struggled. Against Tigers, the outcome depended heavily upon range, impact angle, and ammunition type. German engineers recognized that battlefield superiority could no longer be assumed. The psychological implications mattered almost as much as the technical ones. For years, German tank crews had entered combat believing their vehicles possessed clear qualitative advantages over most Allied armor. Confidence affected battlefield decisions. Crews willing to engage aggressively often achieved better results than those fighting defensively. The arrival of the Pershing threatened that confidence. Now German commanders faced an opponent capable of challenging them directly. Attention then shifted toward optics. German tank sights ranked among the finest in the world throughout much of the war. Companies such as Carl Zeiss produced exceptionally clear optical equipment that contributed significantly to German long-range gunnery success. Naturally, engineers wanted to evaluate whether American optical technology had finally reached comparable standards. After careful inspection, many acknowledged that American optics had improved dramatically, although some German specialists still preferred their own precision instruments. The gap had narrowed considerably. Target acquisition appeared faster than on earlier American tanks. Range estimation became easier. Sight clarity remained impressive under varying lighting conditions. This improvement complemented the Pershing's more powerful gun. A weapon capable of penetrating enemy armor offered little advantage unless crews could consistently hit distant targets. The Pershing appeared designed with that balance in mind. Equally revealing was the vehicle's ammunition storage system. Throughout the war, Sherman tanks had developed an unfortunate reputation for ammunition fires after penetration, leading German soldiers to nickname them with terms suggesting they ignited easily. American engineers had responded by introducing improved ammunition storage arrangements using water-jacketed compartments known as wet stowage. The Pershing incorporated similar protective principles. German investigators examined these compartments carefully. Separating ammunition more effectively from crew positions reduced the likelihood of catastrophic explosions after penetration. No tank remained invulnerable, but survivability clearly received much greater attention than before. Several technical officers reportedly concluded that American designers had listened carefully to battlefield reports submitted by Sherman crews. The Pershing reflected years of accumulated combat experience rather than theoretical engineering alone. Mobility evaluations produced equally interesting conclusions. At first glance, many German engineers expected the heavier Pershing to suffer from the same problems affecting late-war German heavy tanks. Vehicles such as the King Tiger possessed extraordinary armor protection, but often struggled with mechanical reliability, fuel consumption, and transportation difficulties. The Pershing weighed substantially less while retaining respectable protection. Engine calculations suggested acceptable power-to-weight ratios despite the increased mass. Road speed remained competitive. Cross-country mobility appeared adequate for most European terrain. Engineers appreciated this compromise. Instead of maximizing armor regardless of consequences, American designers had accepted moderate protection in exchange for preserving operational flexibility. The suspension system further reinforced this philosophy. Torsion bars absorbed terrain irregularities effectively, improving crew comfort during extended marches. This mattered more than many civilians might imagine. Tank crews often remained inside their vehicles for many consecutive hours. Fatigue reduced accuracy, slowed reaction times, and impaired decision-making. A smoother suspension indirectly improved battlefield performance by keeping crews physically capable throughout long operations. German engineers understood this relationship well because Panther crews had experienced similar advantages compared with earlier suspension designs. Maintenance accessibility continued attracting praise. German armored units frequently complained that even routine repairs required enormous effort. Replacing transmissions in Panthers or Tigers often demanded extensive disassembly. Field maintenance became increasingly difficult under combat conditions. The Pershing approached maintenance differently. Axis panels appeared logically positioned. Components requiring regular servicing remained relatively easy to reach. Internal layouts suggested engineers had consulted mechanics as well as designers during development. This practical approach impressed many evaluators. American industry consistently designed equipment with large-scale maintenance operations in mind. The objective extended beyond winning battles. It included keeping thousands of vehicles operational across entire continents. Fuel systems illustrated another important difference. By early 1945, German engineers knew that fuel shortages represented one of the greatest threats facing their armored forces. Brilliant tanks became useless without gasoline. Entire operations had been cancelled simply because fuel deliveries arrived never. American forces rarely experienced comparable problems. The Pershing's fuel capacity, engine efficiency, and logistical support reflected an army operating under completely different strategic conditions. Some German analysts privately acknowledged That American industrial organization deserved as much credit as American engineering itself. A tank did not fight alone. It depended upon factories, railways, repair depots, spare parts, fuel convoys, and manufacturing capacity extending thousands of miles behind the front. In every one of those categories, the United States enjoyed overwhelming advantages. Communication equipment received equally close examination. German tank doctrine emphasized coordinated maneuvers supported by effective radio communication. Unlike some earlier armies that equipped only command tanks with radios, German armored units had long recognized communication as essential. The Pershing confirmed that American doctrine had reached similar conclusions. Its radio installation appeared reliable, well integrated, and easily accessible for maintenance. Internal communication between crew members also reflected thoughtful engineering. Clear communication reduced confusion during combat, especially when rapid target changes occurred. German engineers repeatedly emphasized that modern armored warfare increasingly depended upon information rather than armor alone. Whoever identified targets first often fired first. Whoever fired first frequently survived. As more captured Pershings became available for inspection during the closing months of the war, technical reports from different units began reaching remarkably similar conclusions. The tank represented America's first true answer to the Panther. Not because it exceeded every German specification, not because it possessed thicker armor than every opponent, and not because its guns surpassed the famous German 88 in every circumstance. Rather, because it achieved something arguably more important: balance. German tanks often pursued excellence in individual categories, even when that created serious weaknesses elsewhere. The Tiger sacrificed mobility for protection. The Panther combined outstanding firepower with mechanical complexity. The King Tiger approached near invulnerability from the front that became extraordinarily difficult to transport, repair, and supply. The Pershing avoided such extremes. It offered good armor without excessive weight, strong firepower without oversized dimensions, modern suspension without unnecessary complexity, effective crew layout without sacrificing protection, reliable maintenance, procedures without reducing battlefield capability. To German engineers accustomed to solving problems through increasingly ambitious technical designs, this balanced philosophy became impossible to dismiss. One engineer reportedly summarized the vehicle's strengths in remarkably simple terms. The Pershing did not attempt to become the world's most powerful tank. It attempted to become the world's most effective one. That distinction mattered enormously. By 1945, Germany possessed some of the most technically advanced armored vehicles ever built. Yet those same vehicles increasingly failed to influence the war because they could not be produced, maintained, fueled, or repaired in sufficient numbers. The Pershing suggested that American engineers measured success differently. They designed not only for battlefield performance, but also for industrial reality. Every manufacturing decision reflected awareness that thousands of identical tanks might eventually leave factory assembly lines. That realization prompted an uncomfortable question among many German specialists: if American industry had produced the Pershing 2 years earlier, instead of introducing it only during the final months of the war, how much sooner might Germany's armored superiority have disappeared? No one could answer with certainty. But for engineers examining the tank amid the ruins of collapsing German cities, one conclusion became increasingly difficult to avoid. The Pershing was not simply another Allied tank. It represented proof that American armored engineering had matured into a direct competitor with Germany's finest designs, and it had done so while preserving the industrial efficiency that had already overwhelmed the Third Reich's ability to compete. As German engineers continued documenting every aspect of the Pershing, their reports gradually shifted away from individual components and toward a much larger question: what did this tank reveal about the future of American armored warfare? For years, Germany had assumed that American industry excelled at manufacturing but lagged behind in innovation. The Pershing challenged that assumption. It suggested that the United States had not been standing still throughout the war. Instead, American engineers had quietly observed every battlefield lesson from North Africa, Italy, Normandy, and the Ardennes, refining a completely new generation of armored vehicles while continuing to produce thousands of Shermans. The Pershing was not simply an upgraded tank. It represented the beginning of a different design philosophy that combined combat experience with enormous industrial capability. One of the most interesting observations concerned production methods. German engineers had always admired precision manufacturing. German tanks were often assembled with extremely tight tolerances, intricate machining, and components that reflected remarkable craftsmanship. However, this precision came at a price. Complex manufacturing required more skilled workers, more machine hours, and more specialized materials. As the Allied bombing campaign intensified, maintaining such standards became increasingly difficult. Factories operated under constant disruption. Transportation networks collapsed. Shortages of steel alloys, ball bearings, copper, and fuel forced engineers to accept compromises they would never have considered earlier in the war. The Pershing demonstrated a different philosophy entirely. Its construction was certainly sophisticated, but engineers noticed that many parts appeared deliberately designed for efficient mass production. Castings minimized unnecessary machining. Welded assemblies followed standardized patterns. Internal fittings seemed organized not only for functionality, but also for ease of assembly on factory production lines. This fascinated German industrial specialists. The Americans had managed to create a significantly more capable tank without making it dramatically more difficult to manufacture. That achievement carried enormous strategic implications. Germany's late-war tanks often became victims of their own complexity. Every improvement demanded additional production time. Every engineering refinement increased the burden placed upon factories already struggling to survive Allied bombing. The Pershing suggested that American engineers had carefully considered manufacturing realities from the beginning rather than treating production as an afterthought. The transmission became another focus of study. German armored vehicles frequently suffered transmission failures under heavy operational conditions. Panthers, despite their outstanding battlefield performance, developed a reputation for drivetrain problems, especially during the early years of production. Tigers also required highly skilled maintenance crews to keep their mechanical systems functioning properly. Engineers examining the Pershing found a transmission that, while not perfect, emphasized durability and maintainability over extreme performance. This reflected a broader difference between the two nations. German designers frequently pushed technology close to its engineering limits. American designers preferred systems operating comfortably within those limits. The result often produced equipment that lasted longer under difficult field conditions. One technical officer reportedly commented that American engineers seemed willing to sacrifice a small amount of peak performance in exchange for much greater operational reliability. From an engineering standpoint, that represented remarkable discipline. Many designers naturally pursue maximum specifications. The Pershing instead pursued consistent performance over extended campaigns. Another aspect receiving close attention involved crew survivability. German tanks traditionally emphasized defeating the enemy before being hit. American engineers increasingly accepted that every tank would eventually face penetration under combat conditions. Therefore, reducing crew casualties became just as important as preventing penetration in the first place. The Pershing reflected this thinking throughout its interior. Fire extinguishing equipment appeared logically positioned. Escape routes remained relatively accessible. Crew spacing reduced the likelihood that a single shell would incapacitate everyone simultaneously. Protective ammunition storage further improved survival prospects. German evaluators recognized these features immediately. Saving experienced crews possessed enormous military value. A destroyed tank could eventually be replaced. Highly trained veterans often could not. Late in the war, Germany suffered precisely this problem. Even when factories produced replacement vehicles, experienced crews had become increasingly scarce. Young recruits received only limited training before entering combat against seasoned Allied formations. The Pershing suggested that American planners understood the long-term importance of preserving skilled personnel. That realization extended beyond engineering. It reflected differences in strategic planning. The American Army expected prolonged operations across vast distances. Protecting experienced crews increased overall combat effectiveness throughout an extended campaign. German doctrine, particularly during the final months of the war, often became dominated by immediate battlefield survival. Long-term planning grew increasingly difficult as military collapse accelerated. Attention then turned toward battlefield repairs. German maintenance officers carefully considered how damaged Pershings might be recovered and returned to service. The answers again highlighted American priorities. Major components appeared modular compared with many German designs. Repair procedures seemed relatively straightforward. Standardized tools handled numerous maintenance tasks. Even battlefield recovery operations benefited from practical engineering decisions. German specialists quietly admitted that keeping Pershings operational would likely require fewer maintenance hours than comparable German heavy tanks. That conclusion may have been one of the most significant findings in the entire evaluation. Winning armored warfare required far more than designing an excellent tank. It required keeping hundreds or thousands of tanks operational simultaneously. Every hour spent repairing one vehicle reduced combat strength elsewhere. The Pershing appeared optimized not merely for combat performance, but for sustained operational readiness. Engine cooling systems also impressed evaluators. During prolonged operations, overheating frequently reduced engine life or caused complete mechanical failures. Germany's increasingly desperate logistical situation often forced crews to operate vehicles under less than ideal maintenance conditions. Accelerating where even further, the Pershing's cooling arrangements demonstrated careful engineering intended to support continuous movement over long distances. American forces frequently conducted rapid advances covering hundreds of kilometers within days. A tank incapable of sustaining such movement possessed little strategic value regardless of battlefield performance. German engineers increasingly realized that nearly every design choice reflected America's operational doctrine. The tank existed not simply to destroy enemy armor. It existed to accompany rapidly advancing armies over enormous distances while remaining mechanically dependable. That philosophy differed substantially from many German heavy tank concepts. The engine itself generated considerable discussion, although not dramatically more powerful than contemporary German engines. Its integration with the rest of the drivetrain demonstrated thoughtful engineering. Power delivery remained predictable. Maintenance procedures appeared logical. Fuel consumption, while significant, remained acceptable for a vehicle of its size. Some German officers initially expected the heavier Pershing to become sluggish under battlefield conditions. Available evidence suggested otherwise. Its mobility compared favorably with several German heavy tanks while avoiding many of their reliability problems. The cumulative effect became increasingly difficult to ignore. Individually, none of the Pershing's features completely outclassed Germany's best engineering. Its armor was excellent but not invincible. Its gun was powerful but not unmatched. Its optics were impressive but not revolutionary. Its engine was dependable rather than extraordinary. Its suspension represented proven technology rather than radical innovation. Yet, when all these elements worked together, they produced something greater than the sum of their individual parts. German engineers admired elegant engineering solutions. Increasingly, they began viewing the Pershing itself as an elegant solution, not because it pursued technical perfection, because it balanced competing requirements with unusual success. Some evaluators compared this philosophy directly with the Panther. The Panther arguably possessed superior frontal armor and an exceptionally effective high-velocity gun. However, achieving those advantages demanded complex manufacturing, careful maintenance, and extensive logistical support. The Pershing accepted modest compromises in certain specifications while dramatically improving operational practicality. Which approach proved superior depended entirely upon the broader strategic situation. Germany in May 1943 had preferred the Panther. America in 1945 clearly preferred the Pershing. The difference reflected each nation's industrial strengths. Perhaps the most uncomfortable realization emerged during discussions about future development. German engineers understood that the Pershing represented only the beginning. Unlike Germany, whose industrial capacity had reached its breaking point, the United States retained enormous resources available for further research and production. American factories stood largely untouched by bombing. Universities continued educating engineers. Research laboratories expanded rather than contracted. Financial resources appeared virtually unlimited compared with the collapsing German economy. If this was America's first mature heavy battlefield tank, what might its successor become after? Several additional years of peacetime development? That question lingered in numerous technical conversations. Some engineers speculated that future American tanks would combine even heavier armor with more powerful engines. Others believed advances in ammunition would eventually matter more than increasing armor thickness. Still others predicted that fire control systems and improved optics would define the next generation of armored warfare. Interestingly, many of those predictions proved remarkably accurate during the decades that followed. Post-war armor development increasingly emphasized exactly those areas. Even as Germany collapsed, Professional engineers continued thinking beyond the immediate conflict. Their responsibility extended beyond winning the current war. They sought to understand the future of military technology itself. Captured Pershings provided valuable clues. By April 1945, however, those technical discussions unfolded against an increasingly desperate military backdrop. German cities fell one after another. Fuel shortages immobilized surviving armored formations. Replacement tanks rarely reached frontline units in meaningful numbers. Even if engineers discovered weaknesses within the Pershing, Germany possessed little ability to exploit them. Technical knowledge alone could no longer reverse strategic defeat. Nevertheless, reports continued arriving from evaluation teams. Some highlighted the Pershing's favorable weight distribution. Others praised its balanced turret design. Several discussed manufacturing efficiency in surprising detail. One recurring theme appeared throughout multiple assessments. The Americans had finally produced a tank that demanded respect not because it excelled in one spectacular characteristic, but because it displayed remarkably few serious weaknesses. That observation contrasted sharply with many previous Allied vehicles. Earlier Shermans earned praise for reliability but criticism for firepower. Churchill's impressed observers with climbing ability yet disappointed in speed. Soviet tanks demonstrated excellent mobility while sometimes sacrificing crew comfort or optical quality. The Pershing avoided many of these trade-offs. Represented maturity. It suggested that American armored engineering had reached a level where compromises became increasingly subtle rather than dramatic. Ironically, German engineers recognized this achievement at precisely the moment when their own industry could no longer respond. Throughout the war, competition between opposing engineering teams had driven rapid technological progress. Each new tank inspired countermeasures. Each battlefield lesson generated improved designs. By the spring of 1945, that cycle effectively ended. Germany lacked time. The Pershing arrived too late to change the outcome of World War II. But it arrived early enough to convince many German engineers that the balance of armored innovation had fundamentally shifted. The nation that had once been dismissed as producing dependable but uninspiring tanks had demonstrated that it could also produce sophisticated fighting vehicles capable of matching Europe's finest designs. More importantly, it could manufacture them using an industrial system that remained intact, efficient, and ready for the challenges of a new era. For the engineers examining captured Pershings amid the ruins of the Third Reich, the implications extended far beyond one tank. They were witnessing the emergence of the country that would soon dominate armored warfare throughout the Cold War. While Germany's own remarkable tradition of military engineering came to an abrupt and irreversible end. By the final weeks of the war, the reports compiled by German engineers had become less about identifying weaknesses and more about understanding why the Pershing had appeared when it did. Many believed that if this tank had reached the battlefield in large numbers during the Normandy campaign or the Battle of the Bulge, Germany's armored forces would have faced a far more difficult challenge. The timing fascinated them. America had possessed the industrial capacity to manufacture thousands of Pershings. Yet it had continued producing Shermans until late 1944. To German analysts accustomed to rushing increasingly advanced designs into combat despite technical problems, the American decision seemed unusually patient. As they studied captured documents and battlefield evidence, many engineers began to understand the reasoning. The United States had refused to introduce an entirely new tank until engineers believed it was ready for mass production and sustained combat. Earlier experimental heavy tanks had revealed mechanical problems, transmission issues, and production challenges. Rather than rushing an imperfect design into service, American industry continued improving it while relying on a Sherman to carry the burden of the war. From a German perspective, this represented a striking contrast. The Panther itself had entered combat at Kursk before many of its mechanical weaknesses had been solved. Its powerful gun and excellent armor made it formidable. But early reliability problems often destroyed more Panthers than Soviet guns. Engines overheated, final drives failed, transmissions broke under combat conditions. Recovery crews frequently found themselves towing damaged Panthers away from battlefields without enemy fire ever touching them. German engineers understood why this had happened. Political pressure demanded immediate deployment. Hitler expected revolutionary weapons to reverse Germany's declining fortunes, and delays were rarely acceptable. Designers and manufacturers had little choice but to introduce vehicles before every technical issue had been eliminated. The Pershing reflected almost the opposite philosophy. Its arrival had certainly been delayed by disagreements within the American army, but once it entered combat, it displayed a level of refinement that impressed even experienced German specialists. They recognized that many of the problems affecting early Panthers had already been addressed during the Pershing's lengthy development process. Several engineers privately admitted that the Americans had probably made the wiser long-term decision. A tank delayed by months but delivered in reliable condition often proved more valuable than one rushed into production before its design matured. Attention soon shifted toward another subject that fascinated German engineers: standardization. Throughout the war, Germany had fielded an astonishing variety of armored vehicles. Panzer III variants served alongside Panzer IVs, Panthers, Tigers, King Tigers, assault guns, tank destroyers, armored recovery vehicles, self-propelled artillery, and numerous experimental machines. Each required different spare parts, specialized maintenance procedures, and unique training for mechanics. The logistical burden became enormous. American forces operated differently. Shermans remained overwhelmingly dominant throughout the war. Even when Pershings arrived, they entered an already organized logistical system built around standardized procedures. Fuel deliveries, spare parts, maintenance equipment, and crew training could all be adapted without completely rebuilding the support network. German engineers admired this organizational discipline. They realized that successful armored warfare depended just as much upon logistics as engineering. A brilliant tank stranded because replacement parts never arrived contributed nothing to victory. One engineer reportedly remarked that America treated tank production as an industrial system rather than a collection of individual vehicles. The distinction mattered enormously. Every Pershing represented not only engineering excellence, but also confidence that factories could continue supplying identical machines for years if necessary. Germany no longer possessed that confidence. Bombing campaigns had shattered industrial centers. Railroads operated intermittently. Fuel production collapsed after repeated attacks against synthetic oil plants. Even when factories completed new tanks, transporting them to frontline units became increasingly difficult. Captured Pershings therefore symbolized something larger than technological progress. They represented an economy untouched by strategic bombing, supported by vast natural resources, protected by oceans, and capable of sustaining modern warfare almost indefinitely. No German engineer examining the tank could ignore that reality. The discussion gradually expanded beyond the Pershing itself. Technical officers began asking broader questions about American engineering methods. Why had American tanks become steadily more capable throughout the war? Why had reliability remained consistently high despite increasing complexity? How had American factories managed to improve quality while simultaneously expanding production? Many of the answers lay outside engineering. The United States had invested heavily in manufacturing science long before entering the war. Automobile companies such as Ford, General Motors, and Chrysler possessed enormous experience producing complex mechanical systems on assembly lines. Those skills transferred naturally into military production. Engineers designed equipment with factory efficiency in mind, because they understood exactly how modern manufacturing operated.